Welcome to our webcast, Wireless for Stationary Applications. I'm your moderator, Mark Hosky, and I'm happy to join you today on behalf of Control Engineering. Now I'm happy to introduce today's distinguished featured speaker. Dan Capano has more than 30 years of experience providing instrumentation and electrical consulting services to municipalities and clients in the private sector. Dan has been published extensively, including a textbook, Network Cabling for Contractors, in 2000, and contributed to the Instrument Engineer's Handbook, providing chapters detailing the use of proprietary data buses and wireless networking technology. Capano is owner and president of Diversified Technical Services Incorporated of Stamford, Connecticut, providing technical services and staffing to the water treatment industry since 1997. He also serves as the president of New York section of the ISA and vice chair of the Stamford Water Pollution Control Authority. He is a certified wireless network administrator. I'm Mark Hosky, webcast moderator and content manager for Control Engineering since 1994. Before we continue, please take a moment to remind yourself about dealing with technical issues during today's presentation. I'll just let you look at this slide for a second. And now we'll go on to my portion of the presentation. In October of 2013, Control Engineering conducted research on mobility, Ethernet, and wireless. I'll review some of the wireless results in the next few slides. Control Engineering performed this research to better understand more about integration, use, and spending for mobility, Ethernet, and wireless technologies, and how they help users of automation controls and instrumentation to be more productive. Results are based on replies from 200 respondents. These technologies are key components in plant-to-enterprise integration, industrial internet, Internet of Things, and big data analytics and optimization, as well as control engineering and automation. I'll go over the summary points above right now. Routers, antenna, modules, and receivers and gateways are the most popular wireless products used, specified, or expected to be specified, with routers being the runaway favorite. Almost 30% of the survey respondents describe themselves as experts. More than 50% have some familiarity with wireless products, and 28% describe themselves as experts. The top 3 wireless protocols used in respondents' facilities are IEEE 802.11n, 58%, Bluetooth, 50%, IEEE 802.11g, 43%. 20% or more used 8 other wireless protocols, although only 2% use WIA-PA and ISA.11a to date. Spending on wireless products and services is strongly correlated with perceived productivity increases. More than half of respondents expect spending and productivity to increase. And the groups not spending as much don't expect as much gain in productivity. (53% of respondents reported that wireless is either somewhat or highly integrated with their controls, automation, and instrumentation at their locations. Looking at the pie chart on the right, only 23% felt wireless integration was easy, 40% called it challenging, more than a third called it difficult or worse. The top benefit of wireless technology is data access, 59%. Second, in a statistical dead heat, are productivity increases, cost savings, time savings, and ease of use. Other benefits include more effective maintenance, better asset management, less downtime, more accurate decisions and processes, among others. Security issues are the largest challenge at 52%. Others include no budget, lack of investment for capital investments, lack of training or education processes to support adoption or integration, too few use cases, and little or no budget. Finally, safety is also a concern. That concludes my Control Engineering Wireless Research Summary. Now on to our feature presenter, Dan Capano. Dan?
Thank you, Mark. All right, thank you everyone for attending this webcast. What we're going to try to do today is give you a very broad treatment of the art and science of Wi-Fi. It's a very complex subject. It's not anything like a wired network, except that it does communicate data from point to point. I'm going to start with a term called pervasive computing. Now, basically, pervasive computing means that computers are everywhere. They're in everything. So consequently, as we're seeing, wireless is everywhere. But of course, your network coverage will vary. And here are the four major categories of coverage that we're all familiar with. And as you will come to know, users demand mobility and access. And mobility is basically bring your own device. This is becoming a way of life. Wireless devices are becoming small and ubiquitous. In 1997, when Wi-Fi was first introduced, it was pretty slow and unreliable, probably topped out at about 2 megabit per second, and it was unsecured. It was open to anyone who could intercept the signal. And because of that, today Wi-Fi still suffers from the stigma of being an untrusted network segment. But by 2012, because of advancements in standardization and the research being done by the various vendors, Wi-Fi has become fast and reliable, secure and protected. So the only other things left to do really are to improve capacity and coverage. So some of the projections that you may have seen: 80% of all data and voice will be carried by the wireless medium by sometime next year. Your home appliances, your cars, they will all be connected, and as you have seen from some of the trade literature, wired telephones are becoming extinct and will be nearly extinct. And for those of my older listeners, what exactly, or I should say my younger listeners, sorry about that, what's a fax machine? They are definitely going the way of the dinosaur. So what are the applications for wireless? Well, they're pretty much limitless. As you can see, there's a long list, which is by no means exhaustive. Wireless can be used pretty much everywhere. And I'll just let you study this slide. This is, again, not an exhaustive list. We'll get into some deployment models later in the presentation, but this is some of the places where you will see or have seen wireless. So what exactly is Wi-Fi? Wi-Fi is an RF technology where instead of using a bounded medium like wires, you're using an unbounded medium such as wireless radio frequency. It creates a lot of different problems. There are several different and competing technologies. We're all familiar with Ethernet and Bluetooth. Z-Wave is a home automation protocol used on the 900 megahertz band that's been widely adopted for home awareness and control. And then, of course, there's Zigbee. It's another IEEE standard, unfortunately not widely adopted. IEEE 802.11 Wi-Fi has, like Ethernet on the wired side, become the de facto network standard. A little bit about the IEEE, Institute of Electrical and Electronic Engineers. Their whole function in their part of the Wi-Fi universe is to standardize features and functionality and to provide a framework for future development and enhancement of the technology. The 802.11 standard was developed by the IEEE 802 Working Group. It allows for a common set of capabilities. It eliminates proprietary operation or deployments. Some of my older listeners will remember Token Ring and Token Bus. These fell by the wayside as Ethernet became the de facto standard. And also standardization promotes interoperability between devices. So the evolution of Wi-Fi, the IEEE 802 project was started in February 1980 to develop computer networking standards. The first 802.11 standard, 802.11 prime, was released in 1994. Very slow and sloppy. It was, as I said before, it topped out at about 2 megabit per second, and it was unsecure. 802.11a and B were released in 1997. 802.11a topped out at 54 megabit per second. B topped out at about 11 megabit per second. Both suffered from very weak security. It was called Wired Equivalent Privacy, WEP. It was very quickly compromised. 802.11g was released in 2004 with the new wireless protected access security. It also topped out at 54 megabit per second. 802.11n was released in 2010. Theoretically has a throughput of 600 megabit per second and has the new WPA2 security algorithm based on 128-bit AES encryption. 802.11ac is in its first draft, was released 2 years ago. Theoretically will top out at about 7 gigabit per second, which will be very, very fast and useful. Security is, again, 128-bit AES encryption. The other big player is the Wi-Fi Alliance. The Wi-Fi Alliance provides certification testing to see if a device conforms to IEEE standards for interoperability and operation. When you see this logo, you can be assured that the device has been tested and conforms to standard and will play nicely with other wireless devices. So speed was the first big hurdle, as I have mentioned. Take a look at this slide. You'll see that we've evolved steadily. The graphic will just give you an idea of how big a pipe you're dealing with from the first iteration to the last. Security was the next big obstacle. Now, I'm not going to get too much into security in this presentation because it is a very complex subject. We will be covering it in great detail in the blog, in a future part of the blog. But suffice it to say that the lack of security in the early deployments of 802.11 were the biggest obstacle to wireless deployment. Again, at the risk of repeating myself, the wireless network was an untrusted segment, and it was not used for anything sensitive, and definitely firewalled. It was not an open network. Well, it was an open network, but it was not a secure network. Newer security algorithms have substantially cured that problem. Reliability is another problem that's come up. Good design makes for a reliable network. Now, what does that mean? Good design balances coverage with capacity. And that means that, if you have a large office, you're not going to provide the adequate coverage with one access point. And if you have 40 people accessing one access point, you are not going to have the throughput. So you need to design for not only for coverage, but for a low user to access point ratio in order to get good quality of service. Also, mobility and portability are very important. A user starting at one end of the building needs to be able to possibly access data as they walk across the entire building without losing connectivity, or to pick up where they left off from one office to another. So the delivery of high-quality data and multimedia demand a high quality of service. Now, QoS is a term that you will see, and to summarize, more users equal more traffic equal network congestion and poor QoS. So the graphic is meant to represent your system administrator pulling his hair out because he can't figure out why you're not getting good video or data. Multiple channels and wireless access points make a reliable wireless network possible. So the inflection points for the development and adoption of 802.11 were first security. The standard that included robust security networks was 802.11i. That was rolled up into the 802.11-2001 standard. It uses a mutual authentication key concept. It fixed the early security flaws of WEP. And then speed was the other inflection point where we proceeded from 54 megabit per second up to 7 gigabit per second. And also included quality of service enhancements to prioritize video and voice traffic using wider bandwidth and multiple radios. And again, wireless will surpass wired speeds by 2015. It is going to be lightning fast. So let's talk a little bit about now the actual science. The radio spectrum that Wi-Fi operates is unlicensed spectrum. Two bands are in common use. The ISM band, which is industrial, scientific, and medical, which is between 2.4 and 2.5 gigahertz, and the unlicensed national information infrastructure band, which is between 5.1 and 5.8 gigahertz. Typically, the ISM band, ISM band is used for a local connection scheme, whereby you would have an access point communicating with local clients, and then the uniband is used for backhaul or long-haul communication, control channels, point-to-point, that sort of thing. It is a lot quieter. It's not used widely, even though with the deployment of 802.11ac, it will become very busy in a very short time. The ISM band has 11 channels in the United States, 13 in Europe and Israel, and 14 in Japan. The channels are 22 megahertz wide, but they're only separated, center frequencies are only separated by 5 megahertz. They will overlap, as you can see in the graphic. So there's only 3 non-overlapping channels that have the required 25 megahertz separation that will prevent the channels from interfering with the other channels' transmissions. The uniband has 23 non-overlapping channels. Channels are 20 megahertz wide. There are 4 separate bands as shown in the graphic. These are 1, 2, 2 extended, and 3. The lower middle, upper middle, and upper. In two of the bands, we need to use transmit power control and dynamic frequency selection because Doppler radar also operates in this particular band, actually in the 2 and 2E bands. Network architectures, there's a lot of different ways to do this, but the four broad categories are autonomous, ad hoc, controller-based, and cooperative. Autonomous access points are your wireless router or a wireless transceiver that communicates with other wireless transceivers. And ad hoc, getting back to autonomous, all the intelligence, what differentiates that particular AP from others is that all of the intelligence, the data handling, control, and management all reside in the AP. An ad hoc network is a device-to-device network that's set up on the fly. A personal hotspot is probably a good example. And you don't need an access point. And it's pretty much managed on the fly by one or two of the different participants. Controller-based uses a central hardware controller to manage the wireless network. The APs typically don't have a lot of intelligence. They handle some data, possibly some control at the edge of the network, but the controller does all of the active management and most of the control of the network. And this could be load balancing of channels, this could be offloading of clients, it could be roaming, that's all the things that require an active control. The problem with a controller-based network is that you have a single point of failure. Unless you build in redundancy at additional cost, you could lose the network, could possibly lose the network if you lose the controller. Finally, the cooperative architecture is something one or two vendors do. The management is distributed. In other words, it's distributed among the APs. Actually, the control and data are. The management is still done with a cloud-based and off-site management cooperative, if you will. The intelligence to build and maintain the network is shared among the APs, and the management is essentially decentralized. In other words, there's no controller to compromise, and if you lose an AP, the other APs will work to take up the slack, and most of the time you won't even notice that it's gone. All right, now the last problem that had to be solved, and this particularly plagued pre-802.11n radios, was multipath. Multipath refers to a phenomenon whereby the transmitted signal arrives at the receiver at different times. Now these are milliseconds, nanoseconds, but it's enough to cause data corruption and unreliable communication. The signals can combine either constructively or destructively. Now what that means is they can arrive in phase or out of phase. If you have something that's 180 degrees out of phase, obviously there's going to be a cancellation. So there is such a thing as constructive multipath, and we'll get into that in a little while. 802.11a, b, and g radios suffered badly from multipath. And I'll just let you check out the graphic. You would be surprised at how many things do cause reflections. So the cure for multipath is to use it. And the technique that's being used in the 802.11n amendment is multiple in, multiple out, or MIMO. MIMO uses a combinational algorithm to utilize the constructive multipath. It also increases reliability by sending multiple data streams or spatial streams, which increases reliability and also allows the receiver to select the best signal. The notation at the bottom of the slide, 3 by 3 by 3, means that there's 3 transmitters and 3 receivers using 3 different radio links, also known as radio chains or spatial streams. 802.11n allowed the use of up to 4 transmitters, 4 receivers using 4 spatial streams. 802.11ac will eventually allow 8 transmitters, 8 receivers using 8 spatial streams. So now some fun stuff. You saw in Mark's presentation that one of the considerations was cost. We've done a few of these implementations, and one of the ways we've sold it is to do some comparative cost analysis. As you can see from this slide, wired networks require a lot more money, as represented by the dollar signs. There is truly a potential of 50 to 75% savings in installation costs alone. We've seen it in real life. Your return on investment is much faster than a physical infrastructure, physical wired infrastructure, owing a lot to the lower cost and ease of installation. Long-term costs are very low. You're talking about units that operate 24/7. All you have to do is provide power. A replacement or upgrade costs are negligible. As we all know, equipment cost comes down over time. And I'll go back to repeating that there are no maintenance costs as opposed to wired infrastructure. But ironically, wireless still needs wires. In any wireless network, you still need to have one access point connected to the wire infrastructure, or you will not have access to any of your outside network resources or internal network resources for that matter. So you still need some sort of a wired distribution system. When the root or portal AP is connected, the distribution can be achieved without additional wiring using the various wireless management systems. We've talked about mesh systems, which form self-routing and healing networks, which greatly improve speed and reliability. And they are theoretically very scalable. Wireless bridges connect physically separated wireless distribution systems, such as in other buildings. We'll get into that in a little while. And this is not so much of a stretch because most facilities at this point have existing wired backbones, or I should say infrastructures. APs also need power. So you do need to provide power, as in all things, even though you can run a lot of APs off of battery and solar. But where AC is not an option, you can use power over Ethernet, which is another IEEE standard. And you can provide 30 watts at 48 volts at 30 watts, or 30 watts at 48 volts, whatever your beliefs are, over Cat 5 or 6 to power a remote AP. The only restriction would be obviously the Ethernet segment length of 328 feet. Again, resulting in dramatic savings in cost, because you don't have to provide AC at a remote location. So we did a cost estimate for a 300-foot trench between a plant control building and an odor control system 328 feet away. And now, without going into each and every line, you can see that the grand total totaled about $25,200. This does not include design services, appurtenances, management, and IT configuration, which can easily bring it up over $30,000. Now, using wireless, you can see that the cost is substantially lower. And this cost of, say, let's call it it's $64.20, let's call it $6,500 by the time it's all said and done, includes all management, configuration, and appurtenances. It is really, in our opinion, a very cost-effective solution, especially when you're looking to replace an aging physical plant. And the thing about wireless also is that designed properly, distance restriction is not an issue. You can theoretically have unlimited range. Again, APs can use PoE, local power, battery, or solar, and unlimited number of wireless devices can access the medium, of course, if it's designed properly. So to summarize, the wired link without any overhead cost ran about $25,000. The wireless link ran about $6,500. Savings of roughly $18,780 or a 4-to-1 ratio. Almost a 75% savings on installed costs. So a couple of words about deployments. Wireless hotspot deployment is probably the most basic model outside of the small office, home office model. It's based really on coverage, not capacity. The graphic at the right-hand side shows an example of a secure internet portal login, which gets everybody's attention and pretty much puts them on notice that if you do anything illegal, we're not responsible, and you will be prosecuted. Security is typically not provided by the owner of the AP. This is something that the client has to worry about himself. Being as users are transient, it's not really all that important either. And it's a common marketing tool. Retailers can break into transmissions or pop up an ad saying, 10% off your next cup of coffee in the next 10 minutes, that sort of thing. So it is a very useful tool for retailers and coffee shop owners, if you will. The auditorium stadium deployment model. Coverage and capacity are primary design goals. You will need quite a few access points. These are typically controller-based networks. Directional antennas are a must to make sure that coverage is strictly controlled. One thing that you'll come to realize is that the human body does attenuate radio waves. So that becomes a factor when you're dealing with a large group of people, particularly in an auditorium. Security is absolutely mandatory. The systems must prohibit device-to-device connectivity, which means that the guy sitting 4 rows above you cannot hack into your phone. Fosters augmented reality. That sentence could have been better, but all that means is if you look at that icon down at the lower right, we've seen this in some deployments where you can take a tour of the facility, show you where the bathrooms are, where the bars are, what specials are being run in the gift shop, that sort of thing. Classrooms, which is a tremendous market for wireless. Coverage is primarily the design goal. Capacity is a close second, but it's not very crucial. It's crucial in terms of multimedia delivery. Attenuation from bodies becomes another factor, as we just mentioned. The coverage issue becomes dicey, to put it bluntly. You need to contain the RF because the adjoining classroom is also going to have a wireless AP, and you don't want these two to interfere with each other. So a multi-channel architecture, which is something we'll talk about in the blog, versus a single-channel architecture. A multi-channel architecture uses the different overlapping channels in order to avoid interference. between the adjoining access points. Directional antennas are also used. Transmission power control are also used if not required. And it allows a lot of flexibility for educators. Another deployment is bridging and point-to-point. Bridging simply means that you're connecting two networks that are separated by some geographic distance where it would be prohibitive to install wiring. This has been done, this is probably one of the earliest deployments of Wi-Fi or RF technology. Theoretically, there is no limit to the amount of remote wireless or wired distribution systems you can connect to or their distance. It all comes down to understanding the principles of RF propagation and how to apply them. The case study we're going to go over is the Stamford, Connecticut Water Pollution Control Authority plant, where we are researching the viability, or I should say, we're promoting a proof of concept project that will show how wireless is a viable alternative to wired network connections. We're actually well into this project. It is working very well. We have two access points spaced at about 300 feet away from each other. We're using a 802.11 to 802.15 translational bridge to connect 802.15 wireless HART sensors, or I should say transceivers, to the 802.11 wireless network. It's working very well. We did start in April. It is running at this point. We're very pleased with the results. Just a shot of the Water Pollution Control Authority. It's about 800 feet wide by 1,500 feet long. This graphic shows the placement of the two access points. The access point in the center of that coverage area, that orange area, to the lower right is where the odor control system is, that from which we're monitoring ORP, pH, and level in the sumps. The other access point up to the upper left is the control building where the control room is. That is the wired portal. This is a mesh network. There is no wired connection between the two of them. The coverage shown is a predictive coverage. In other words, we used a predictive software, a predictive survey software, which we'll get into in a minute. The coverage is actually much, much better than we're seeing here. It does follow it closely, but it is very impressive in the coverage and reliability and quality. This is the full deployment that will happen probably within the next year. We'll be adding 3 more access points to improve coverage over some of the process areas. Again, this is predictive. Now we'll get into a little bit about site survey, which is what you just saw, a predictive versus manual survey. Predictive surveys are done off-site, manual on-site. The survey maps that you just saw, let me go back to this one. This is based on the materials of construction of the various buildings. It is set for free air because we are running an outdoor network. But you will see where some of the shadows are created. Now, when we went back to do the manual survey to check our conditions, we found that the predictive survey was good, but not as good as the actual coverage. Manual surveys will identify sources of interference and the presence of other networks. So, and interference is the chief cause of network connectivity and capacity problems. If you have another network running on the same channel, then you are going to experience some problems. And this is why you should always go back and do, one of the reasons you should always go back and do a manual survey. The attenuation of common items. This is something, there are charts out there which are much more detailed, but you will see that these are the most common materials you'll run into. Free air has, I don't think that's correct, but we'll look into that. Okay, pre and post deployment surveys. What you saw a few slides ago was a pre-deployment survey. And it was a predictive survey. Post-deployment surveys are always manual and are always used to check predictions and to tweak network coverage. You may have to move an AP, you may have to move partitions. This is why post-deployment should always be done under actual conditions. If you do a post-deployment survey on a Sunday when no one is there, you've removed a lot of the source of attenuation, and that is the bodies, the use of cordless phones and microwaves. So these are the things that you need to get in there on an actual workday to do. Surveys are essential for good design and performance, not only for that particular deployment, but for lessons learned. Once you get in there and actually find a problem, you have a problem, and stand there scratching your head. At some point, you're going to say, yes, I remember. At one point, this is what happened, and this is the problem, and this is how we solved it. And a periodic survey and audit should be performed at least yearly, because offices change, the population of offices change. You could be having problems with an AP. You could be having problems with your wired plant. So it's good to go back and check. So what is the future? Well, AC is upon us. Most of the routers that you see and most of the APs that you see are now AC compatible with the first draft. They will come in waves. The final wave will be quite fast. 7 gigabits is the prediction. AD is going to operate in the 60 gigahertz spectrum. It's multi-gigabit throughput, wide bandwidth, and very short range. It's still in draft. 802.11af uses the white space in TV transmissions for high-rate, long-distance transmission. Well, I want to thank you for your kind attention, and I'd like to turn this back over to Mark and answer any questions I can.
Thanks very much, Dan. Appreciate your comments and your teaching today. For those attending the webcast, let's take some questions. The audience can type questions for today's presenter in the Ask a Question box on the screen. We'll get to as many questions as we can. Also, questions were submitted with the pre-registration, and within a few days, the presentation and the questions will all be available for on-demand viewing. We'll post the archive on the Control Engineering website, and we'll send an email message with a link connecting directly to it and to related resources after it's ready. Dan mentioned a couple of times the blog. He had such good material in the presentation here. He's going to extend his learning with a new blog on the Control Engineering website on the topic of industrial wireless tutorials. With the registrants, more than 60 questions were submitted as of last week. I categorized them and counted. Of those, the top 5 areas were design and application-related questions were the most common, followed by security-related questions, interference and reliability, safety, and troubleshooting. And I can see the questions on my screen deal with those as well. So Dan, we'll get right to it. The first question, let's see, do you have advice about access point and antenna placement? AP, you talked about quite a bit with the application, which was very illustrative. I like that a lot.
Well, You know, every deployment is different, Mark. When you come into an office or into a facility, it's really up to the practitioner, the designer, to walk around, have a look at the way the place is laid out. You obviously want to avoid objects that will attenuate RF. You want to avoid a lot of concrete, steel, steel partitions. Elevator shafts are particularly notorious for RF attenuation. If you have long hallways or long rooms, directional antennas are definitely an option that you should consider. They will not only will they sculpt, if you will, the RF energy into a specific area and eliminate spillover into areas that you don't want, but it'll also amplify the signal. Microwave ovens, I just want to say another word about microwave ovens. We always laugh about it, that people would say, you know, it seems strange that I lost my Netflix feed when I smell popcorn. And we laugh about it, but it is very true. Microwaves operate in the 2.4 gigahertz range, and some of the older ones are very leaky. You've seen them, and they will interfere with your Wi-Fi transmission. So my advice is to get the lay of the land, place your APs in open areas where there are no opportunities for gross attenuation, and in certain situations, remember that directional antennas are sometimes your best option.
And I've heard that loading docks can be a particular, if you have a manufacturing site and trucks coming in and full, is certainly different than maybe a weekend situation.
Well, sometimes you have to consider dedicating an AP to a certain area and possibly more than one AP at lower power. I mean, just because you have an adjustable power setting on an AP doesn't mean that you have to run it at full tilt. Sometimes lower power levels with directional antennas can get you around some very difficult situations. Another deployment would be warehousing, where you have a lot of stock and you have a lot of metal shelving. It is a nightmare to provide adequate coverage, adequate reliable coverage. So typically in that situation, and in the loading dock example, you would use lower powered APs with directional antennas that you could actually aim the RF energy into the areas that you need it.
Great. The next question leads right into that answer, and that is, what are some key pointers to avoid interference and improve reliability?
Well, again, you do need to design for adequate capacity and coverage. The user to AP ratio, I would say no more than 20 to 30 users or devices per AP would probably be a good starting ratio. I mean, all deployments are different. You want to avoid the microwave ovens. You want to avoid the cordless phones. You want to keep APs away from any source of interference that would start to affect the transmissions negatively. So, I mean, it becomes almost intuitive when you see what you're dealing with, and you start deploying these networks. You start to get a feel for where you can put these, where you can put the APs to avoid the most gross interference. The other thing to do is you need, if you do experience that sort of thing, you need to get some specialized test equipment, such as a spectrum analyzer, to see if you have another network somewhere in the neighborhood who's on the same channel as you. It's not all that common, but it happens, and sometimes you have to bring out the big guns to figure out exactly where the noise is coming from.
And your idea of the mesh design in some applications can be good, because if there's temporary interference with one access point, the mesh can compensate for it.
That's true. Mesh networks are particularly well suited to control applications, I've found, because they are very robust. They are self-forming and healing. They will, if they find that an AP is having a problem communicating, they will find an alternate route or a low-cost route, if you will. That's an expression you will hear, the open shortest path first or least cost path first. This is something that's built into the algorithms that control the mesh and allow for much more robust and reliable communication.
The next question deals with advice about troubleshooting wireless networks. Certainly having the right kind of instrument to check for another network nearby, as you mentioned. Are there other tricks of the trade?
Well, again, it goes back to what I was saying about getting a feel. Once you have an idea of how your network, works and what the capabilities of the equipment are, and what the attenuation factors of the different materials are that you're dealing with, you'll find that it will occur to you. Maybe I shouldn't put the AP behind this wall, or maybe I shouldn't put the AP behind this elevator shaft, or something along those lines. But troubleshooting, the simplest thing you can do, and this is something that a lot of people overlook, is simply reset your wireless adapter. And I would say not 9 times, but 8 times out of 10, that cures the problem. Sometimes you have to reset your TCP/IP stack on the computer. That sometimes clears up the problem. You will have an issue sometimes where there's not enough APs, which only means that there's not enough coverage, and there is a phenomenon called near-far, where the client device can hear the AP, but the AP cannot hear the client device. Without getting too far into the medium arbitration aspect of this, which I will cover in detail in the blog, if the other stations do not hear, and when I say stations, I mean client devices and APs, if they do not hear a particular station transmitting, then they will assume that the medium is clear and they will start to transmit, and that causes nothing but problems for everyone. So these are some of the things you can come across. Again, using a spectrum analyzer is helpful if you suspect that there's another network stepping all over yours. Many, I would say the majority of problems occur because of a poor design and interference. So those are the 2 things that you should look at right from the get-go.
Good. Can wireless be used in hazardous locations or for SIS, safety instrumented systems?
Well, of course, you have to observe the rules and regulations for hazardous location deployment. The APs should be intrinsically safe or rated for a Class 1 Div 1 or Div 2 environment with the proper enclosure. NEMA 7 enclosure would be, of course, required. So, there's nothing inherently bad about RF. They're low-power devices, relatively speaking, but you want to take all the precautions that you would for any other piece of electrical equipment in a hazardous environment.
Great. Well, thanks, everyone, for the great questions. Again, we'll answer some of these offline and post them along with the registration area and the link to the blog directly. Thanks again to our great speaker, Dan Capano, for sharing his time and expertise.